Another one for the last one here. Okay, this is Kolmogorov-Arnold networks, which I just learned about like 3 days ago. They're all the rage. There's a ton of papers about them this year because these are supposedly going to replace deep neural networks. Now, what we've been doing is deep neural networks. Let me go back to one back here. This one here, I think, at the bottom. Yeah, this one here at the end. Yep. Okay, this is a deep neural network. You have input, then you have a hidden layer of neurons, then you have another hidden layer of neurons, and you might have a bunch of these, then you have an output layer. So all these inputs affect all these neurons affect all these neurons, so now you can do amazingly complicated things, but you don't know what's going on. If you say, what exactly did this weight do? Nothing explainable. So it's not interpretable. The KEGG fixes this. All right, so we're going to do it in 2 steps. First, we're going to talk about standard curve fitting by least squares. So if you want to fit data, this is without neural networks. All right, so we're going to fit a polynomial. So you have some data polynomial with some noise, and then you fit a polynomial. And this is actually how I started with this stuff maybe 50 years ago. This is a solved problem that's been around forever. If you want to minimize the squared deviation between points in data and the input function is a polynomial, you can solve it analytically. You don't even need a computer. You can just calculate the parameters from a simple calculation and find the best fit. And that's why this is default in Excel and everything else. By the way, I should mention something. If you try to fit this with a polynomial, you don't know what order to use. If you use a high order polynomial, like a 10th order polynomial, it will have a lot of waving up and down. So you might be able to fit this wavy data here. Now the problem is, if you have a gap in the data, the high order polynomial will have a lower least squared error, but it will have weird things like if you wanted to fit this data, and then down here, it might go way down here and way back up. It has these curves. There's even a name for these things. It tends to have these wavy spikes that go away from the data because higher-order polynomials like to wave around, and all you told it to do was minimize the squared deviation of the observed data. So in between the data, it's allowed to do anything, and it will cheerfully do something ridiculous and not be smooth. And this, by the way, is what happened to Donald Trump. You may remember in the early days of the COVID pandemic, Donald Trump first had just 3 cases, it's just 6 cases, and then he said, oh, it's going to vanish in a month on Easter. It'll just fall to 0 and be gone like magic. Because somebody in Donald Trump's cabinet was a financial analyst, and they fed the COVID data into Excel, and they fit a polynomial to it. And the polynomial fit the things and then just went to 0, which they'll do. And so that's why he thought it was going to go to 0. The unnecessarily high-order polynomial had that effect. Anyway, so here, if the degree is too low, if you try to fit it with a straight line, then you'll have systematic errors, and you can see the sum of the squared errors are up here. The residuals are 1200, that's the sum of the squared deviations. If you fit a straight line through, the residual is now 6900, and you can see why. These are all above the line, these are all below the line, these are all above the line. The data is curved, but the fit is straight, so you never can do a good job. If you make the degree too high, the residual will get smaller. This is a residual degree of 3, you hardly notice the difference. Degree of 9, it starts doing this waving around stuff, fitting the noise in addition to the data. So the residual will get smaller, but you're not actually modeling the underlying phenomenon, you're fitting the idiosyncrasies of your particular noisy data. All right, and then you can do ones with fewer lines stuff. So that's least squared fitting. Now, we're going to try to do this with neural networks, the way we did before, but we're going to do it with explainable neural networks. That's what these CANs are. So the CAN works like this. We fit with these things called B-splines. And splines work like this. A zero-order spline, you take some reference points. We're going to take 20 evenly spaced reference points between -1 and 1, and we're going to try and model this wavy curve here. A B-spline of order 0 simply takes the value at the reference point, and any point near there gets the same value. So it's always a horizontal line. So you model it with just these blue horizontal lines, which of course is pretty miserable. And this is not that different than what we saw before, which you get with like a B tree, with a tree, neural net. But that's a spline of order 0. A spline of order 1 just draws straight lines between the reference points. And as you can see, it gets a lot closer to fitting. A spline of order 2 draws parabolas through each group of 3 points at the reference points. And a spline of order 4 or order 3 takes 4 points in a row and fits a cubic through them. So you take, now the thing about this, there's another way to represent this, which is what you're going to do is simulate the curve with a sum of basis functions. And the basis functions look like this. For order 0, the basis functions are 0 everywhere, like the red one is 0 everywhere and 1 in this region. And the green one, you can't see the bottom. Green is only 1 here and only 1 here. Those are the basis functions, simple square waves. And then you just add those together with weights, and that's your model. That's all this is. If you have these things and you have a weight for each one, then you can do this. You can have a horizontal line, put it the right height to model the models. That's how you do it. And with those basis functions, you get a pretty measurable fit. Here's the linear basis functions. You use these trees that are just straight up and straight down and limited to a certain region. And you spike the data with that. And then here's the second and third order basis functions, which are similar. And the point is now, you can model it with this, and that's what we had up here. The model can produce a pretty good fit. And the point is, you can explain it now because each one of the parameters only affects a limited range here. So if I want to know why is this too low, I could answer that question. I can find, well, it's got to be the parameters of this basis function around here. All this stuff over here is not contributing at all to the result there. Now, the reason it's low, of course, is because it's near the edge, and I cannot make a cubic by taking 3 points over here and 1 point here. So what you really need to do is extend your reference points a few points to the edge. But the point is, you can explain what's going on now. If you don't like what it's doing here, you know which parameters control the behavior here, and all the other parameters don't matter at all. And it turns out you can do all the machine learning things with this stuff, and they're explainable, and therefore presumably more controllable. And this should solve the problems like the catastrophic forgetting, where when you train it, fine-tune it with new data, it forgets the old data. That's the kind of thing they're hoping you can address with these KAG networks, as opposed to standard neural networks. So that's why this is the new hotness. Everybody's working like crazy on these CANs now, hoping that they'll make powerful models more interpretable than the neural nets we've been using, which are called multi-layer perceptrons. They're also called deep neural nets, where you have layer after layer of intermediate neurons, and you don't really understand exactly what they're doing. By the way, I used to work on the human brain and modeling and stuff, and the same thing's true of the human brain. We would like to say, at the first level of your visual system, you find the edges, and then you find the shapes, and then you combine the shapes to mean things, but that's not really what you find when you look. You find like what you'd find in a computer. Some kind of combination of inputs is used to make some kind of abstract thing here. And for example, if you show someone a picture of Johnny Depp, there is one cell in their brain that fires. You do have specific cells to recognize the faces of famous people. Not just abstractions, but really just that face, because of course evolutionarily recognizing who's in your family and friends and who is a stranger is important. So your brain has adapted to be very good at exactly determining whether you've seen that face before, which is a level of abstraction that is hard to model in simple terms of like edges and contrast and stuff. Anyway, that's what I wanted to show you. Let me stop this recording.